AI intern at the CellStrat. Today I will give a brief overview of the state of quantum machine learning and how it can be useful in the overall machine learning scenario. So, yeah. Why quantum is different? The fundamental aspects that differentiate the quantum and the normal computation is the unit of computation. That is, classical bit has only two states, whereas quantum bit or qubit has multiple states. Can be in a superposition. Simultaneously, it can be 1 or 0, and thus it increases the computational path, so to say, and that will increase the computation speed exponentially. Second phenomena is called entanglement. So in an entangled state, if two or more qubits are entangled, then their states are connected to each other. So one qubit is at state 1, the other qubit maybe also at state 1. So if one qubit changes its state to 0, the other qubit will also reverse its state. Right. So that phenomena is called the entanglement of qubits. And yeah, so that phenomena is called the entanglement of qubits. And when number of qubits are, so there can be entanglement between number of qubits, not just 2 qubits. So there can be entanglement between the thousands and millions of qubits. So with this entanglement, if the state of one qubit changes, so immediately without any kind of delay, even there is not a delay of nano or micro or picosecond, and without any delay, the state of entire millions of qubits changes. So that is what gives the power for computation. So as you can see in the digital computation, if one state of transistor changes, so to propagate that change in the state to the next transistor and next transistor, it takes time, and that extra time that is elapsed during the transition of states, that is what delays the computation. So if there is an algorithm which requires millions and millions, billions of computation, so this delay in the change of state of bits versus delay, there is no delay in change of state of qubits. So that delay in the change of state, that's what delays the computation, and that's why the quantum computers are so powerful, and they can compute the billions of computations within a few milliseconds or few seconds, which a normal computer will require about thousands of years. So that's why there is so much interest in the quantum computation. Well, entanglement. So what are the types of algorithms that can be used? So in a classical scenario, the data is also a classical, and a computation is also classical. Whereas in the CQ scenario, the data that we feed to the computer is classical. We have to convert it to the quantum data, and that quantum data is fed to the quantum computer, and when the result is arrived, the computation can be converted back to the classical data. So this is the most popular form of computation right now, CQ. In QC form of computation, type of algorithm, there is a quantum data and it's processed with classical computer. Whereas QQ computers, there is a quantum data, and the quantum computer is used to process that data. So most popular one right now is the CQ. We convert the classical data in the form of bits to the qubits, and those qubits are fed to the quantum computer, and those quantum computer will process the data and give back the result in quantum data, and that quantum data is converted back to the classical, and we can see the results. So this is the most popular type of algorithm. So let's see basic representation of qubit. Why this is very important. So as you can see, this is the state of qubit here. So if this is the state of qubit here, so its state is given by probability alpha that it is at state 0, and probability beta that this is at state 1, where alpha square plus beta square is equal to 1. And alpha is given by this theta angle, cos of theta by 2, and beta is given by this angle, this psi e to power psi and sine of theta by 2. So this is the representation of a qubit in a Bloch sphere. So this is the basic thing. So let's see, similar to what we see in the classical computation, there is an AND gate and NOT gate, OR gate, and various type of different gates in that do manipulation on the bits. In case of qubit, we have the quantum gate, and the quantum gate poly X, it will turn the qubit into a phase. So we have to remember that this qubit operates in a three-dimensional space, whereas a bit operates in a two-dimensional space, or probably single-dimensional space in either 1 or 0, whereas qubit can be operates on a three-dimensional space. So that's why there are a lot more operations that can be done on a qubit. So we can rotate this qubit in X, Y, or Z direction. And Hadamard gate, this is phase shift gate, C0 gate that operates on two qubits, where one qubit is used as to control the operation on the another qubit. So swap gate is a swapped state of two qubits. Toffoli or CC0 gate, which operates on the three qubits. So there are various quantum gates that can be operated on the qubits. So let's see what is a quantum algorithm. So in quantum algorithm, multiple states, qubit 0, qubit 1, and qubit 2. For example, there are 3 qubits. So they can be operated on time on the various gates. So this is how we draw the quantum algorithm or quantum circuit, which is sort of synonymous. So teleportation algorithm we have seen. So in this, what happens is qubit 0 will transfer its information to qubit 2 after the operation. So whatever was qubit 0 state, if it is 0, then qubit 2 will be also be 0 at the end of operation. If qubit 0 is at state 1 or at in between state, superposition state, then the qubit 2 will be at the same state at the end of the operation. So this is called teleportation of information from qubit 0 to qubit 2. All right. So no questions.
Audience, feel free to ask any questions if you have any.
Yeah. So variational circuit. So what is a variational circuit? That is very similar to a neural network. So in a variational circuit, there are multiple parameters of qubits that can be programmed so that it can give the appropriate output. So in this state, what we do is we prepare the data and convert it to quantum data, and this quantum data is fed to the circuit, uh, whereas theta and phi alpha are the trainable parameters. So what happens in the variational circuit is whatever output we get, we compare with the uh, expected output. Essentially, it's supervised learning. So we compare it with the expected output, and once that part we find out the loss or error in the output, we give back and train the parameter theta. So that is essentially we change the parameter theta and try to execute to the algorithm again. So it's essentially similar to training weights in a case of the neural network. So this is sort of called the quantum neural network basic building block for creating the quantum neural network. So yeah, so that is the basic variational circuit where we have trainable parameters and that can be trained to get appropriate output. Okay, so yeah, to summarize this, I just show so can use the quantum computing in machine learning, and that can exponentially speed up the calculations. So entanglement and superposition are the two key phenomena which enable quantum computing. So most feasible way right now is to use the hybrid model of computing, where classical data is converted to quantum data and processed in a quantum computer, and then result is converted back to the classical data. So yeah, just to show you the demo, so I created this MNIST classification using the quantum variational circuit.
You can increase
So
the font a little bit and you can walk through it. We have some time.
okay, yeah. Yeah, so it took about 2-3 hours to execute and run. So yeah, this is just the basics. This is the pre-processing. We are just fetching the data, MNIST data for classification. To remove contradiction. Yeah. Pattern. So here we are creating a grid qubit, 4x4 rectangle, and enumerate and append. So here is our grid qubit, which will train it. So essentially, we have 2x2 qubit family, 3x1 qubit family. We are feeding the data to the grid qubit array. So here we have layer builder. With data qubit will create. So in symbol, it will create a qubit structure, and yeah, so here we have multiple qubit structures. So this is operated on the 4 qubit. So we have here 2x2 qubit array. So yeah, so we here the various operators. So this operator works on input xx minus 0 and this to the power input x. So here in each step, the circuit goes to the next parameter, the next level, and it will operate on the previous data that is coming into the input line. So here we train the model. So this is our model parameters. So we just train 3 epochs. So this is comparison with the classical model. So here we have typical classical Keras model, which is doing essentially the same thing as MNIST data. So we are comparing basically the quantum and classical. So here you can see that classical accuracy is little bit more, but the speed of computation. So since this is a strict simulator, so essentially there is not much of a difference in computation time. But yeah, once we execute it on actual computer, quantum computer, so that time the computational speed will exponentially increase, and we can increase the number of qubits. So essentially we can increase the number of qubits, and we can get a more accurate result as compared to the classical one. So right, that's it from my side. So any questions here?
Yeah, the last two slides were relatively new. I haven't seen those. If you could explain them. Yeah,
This one.
yeah. So these, yeah, this one and the next one. So what's going on here?
So this is just a quantum algorithm for teleportation circuit. So what happens is this is how we basically represent the quantum circuit. So what happens here is, so qubit 0 is, this is the time stamp. So the qubit 1 is basically qubit 0 and qubit 1 are in a classical state initially, that is they have some classical information. So and qubit 2 also they have some classical information. Now qubit G1 here is put it in a superposition state. Superposition state means so we have seen superposition state means basically it is at superposition state means essentially this is at this alpha and beta are yeah, superposition means alpha square is equal to 0.5 and beta square is equal to 0.5.
Yeah, Neeraj, are you
So
there?
yeah, can you hear me?
Yeah, yeah.
Right. So superposition state means 50% probability that the state of the qubit is at state 0 and 50% probability that state of qubit is at state 1. So that is called superposition state.
What is this word teleportation?
Yeah, teleportation means transporting the information from one qubit to another. So in classical sense, I don't know if you have seen the Star Trek or something, then they teleport a human being from one place to another. But this is teleportation of the information, not teleportation of the matter.
Okay.
So basically, it's transferring information from one qubit to another qubit. So all these qubits are in entangled states and they may be thousands of miles away. Right. So here what's happening is first qubit goes to the superposition state and then C naught. So depending on what is the state of qubit 2, this superposition state is so this
So this is
depending on
conceptual representation, right? So in physically, how will it be? What will be the architecture look like in the physical world?
a physical
So
world.
this will be within a quantum computer, or it will be across quantum computers, which could be
It can be
geographically
across
distributed.
it can be geographically distributed. Uh, for example, one qubit can be in Bangalore, other qubit can be in Delhi.
Hmm.
So essentially,
Okay.
whatever is the information? Suppose you want to take a picture from cat and mouse and send it to Delhi. So right now, what we do is we take a picture and there is a you want to send it to Delhi. There is a delay of few milliseconds and all. So yeah, that is the problem. Though it is the internet is like as fast as very fast is megabits and gigabits, but still quantum internet can be a lot faster than that. It's instantaneous. So yeah, in this case, the qubit 0 can be in Bangalore, qubit 2 can be in Delhi, and the information of the qubit 0 is transferred to the information to qubit 2, right? So that is the teleportation circuit.
Okay.
So this is essentially useful for creating the quantum internet. So
All right. I
variational
think there is some time. So if you like, you can review your paper as well if you are interested. Yeah, variational circuit, correct.
yeah, so variational circuit have the trainable parameters where it's similar to what we do in the mm, in the neural network. So there we get some input, then process the data and give some output, and essentially we compute the cost and give the feedback loop to the weights of the neural network, and those weights are adjusted or sort of trained in the next iteration. So after each iteration of training, we get more and more accurate output. So variational circuit are similar in that sense that we have a parameter theta which is a trainable. So the quantum circuit operates on this input parameters inputs, and there are trainable parameters inside the circuit, and this will give us the output in terms of classical information. So this with here we compute the cost function and find out error from the input to the output. Sorry, expected output versus the current output, and from that we find the error and we give the feedback to the input where the parameter theta is trained again. That is the state of the qubit, or it can be state of multiple qubits. So this can be trained again, and this way we can create a quantum neural network. So this is essentially the basic form of quantum neural network, and we can have very complex quantum neural networks with hundreds of qubits. But of course, we have to do the actual calculation and see how it operates exactly.
There are some questions in the questions tab.
Okay, can you give some real-time examples where quantum ML is very effective? There are, as I said, the quantum computation will exponentially speed up the computation time. So whatever the calculations that are required, that require about 2 hours or 3 hours of training right now, that will be trained within few milliseconds or few seconds. So currently the quantum computers are not that practical. So it is difficult to give real-time examples of quantum ML where it is currently used exactly. But yeah, the current projection is that within next 1 or 2 years, quantum computers can be a lot more stable, and we can actually use this quantum computers for doing the quantum ML. So those algorithms now, if you require suppose 1 week to train a ResNet, so that uh, can be done. That can be done in a few seconds instead of weeks. Due to the binary classifier, it's not a binary classifier. The digits are 0 to 10. So there are 10 different states for the digits and 10 different digits, and I'm creating the MNIST output of 10 different states here. Okay, so it's not a binary classifier. How to convert the classical data into quantum? How do you decide the qubit size? I have explained it in my paper how the classical data is converted to the quantum data. So there are basically various techniques which can be used to convert classical data into quantum data. So I have explained it, basis embedding or amplitude embedding and all that. I have explained it in the paper mostly. How do you decide on the qubit size? You mean number of qubits? How many qubits are required? So that really depends on your trial and error method. There is no hard and fast rule where how many qubits are actually required for to do the computation. But based on the computational requirement, you can guesstimate how many may be required. What are the trainable parameters? So trainable parameters are essentially similar to the weights in the neural network. So weights are the trainable parameters in a normal neural network, whereas angle and amplitude of a quantum amplitude is always one, but angle and state of the qubit is a trainable parameter in case of a quantum computer. So yeah, any more?
Okay. Yeah, you can just scroll through your paper from top to bottom. Don't have to talk. I think you spoke most about the topics, but you can scroll through the paper. And I'm just looking for an option to share the PDF document here with the audience, but I'm not seeing right here.
Yeah, in quantum training also we use gradient descent algorithm, so that is applied to the quantum computer. So, yeah, this is basically how the state of quantum computation. This is basically information about how the qubit is represented, then the description of the quantum gate, and then here I have explained how the data is converted from classical bit to the quantum bit. And here this you can see how this quantum data can be used in a quantum circuit. And here I explained about a variational circuit. Yeah, so some of the libraries that can be used for doing the quantum computation: TensorFlow Quantum, PennyLane, QSkit. QSkit is there from IBM, and there are a lot of other packages available from Rigetti and all that, which are specific to those. From Microsoft also there is a Q# language similar to C#. So yeah, they have Quantum Programming Studio. Microsoft also has Quantum Programming Studio. Yeah, so the various companies are pushing their own technology or their own language or their own development stack SDKs for development of quantum computing. Yeah.
So I'm just trying to share through Google Drive the paper link with the audience here. Just a moment. You haven't updated the paper recently, have you?
No.
Okay. Okay, got it. So I'm just going ahead and sharing the downloadable PDF link with the audience here. Okay, so friends, I have shared this paper, the PDF, in the chat, and you can explore it or download it. It's a PDF document, so by tomorrow it should also be available on CellStrat paper section website. But meanwhile, you can download it from this link. Okay, so a nice presentation. Audience, any other questions for Neeraj here?
Yeah, let me know if you want to join our quantum machine learning group, and we can create new algorithms for quantum computers.
It's a whole new ocean to capture. So we are very interested in growing the quantum research effort. So reach out to us if you're interested and want to work with Neeraj and try to research this area and create a whole portfolio of research as well as products in this space. Okay. So any final questions for Neeraj here? Okay, so I guess there aren't any questions. So thanks a lot, Neeraj. Excellent paper and session. And look forward to more quantum research from you. With that, let me go to our next presenter. Neeraj, you have any final comments, or are we done?
Done. We can do. We're done.
Okay. Thank you, Neeraj. Thanks once again. And with that, I go to our next presenter, which is Gautaman Ashokan, and he is an AI researcher in our AI lab. And let me make Gautaman the presenter. Hi, Gautaman. Good morning. How's it going?
Hi guys, today the topic that we are going to be seeing on is graph convolutional network. So I will just give a brief introduction of what is graphs actually. So graphs are essentially a relational data. So it actually consists of nodes actually and edges. So when you have nodes and edges, it forms a graph. So this forms a graph where these represent the nodes and these represents the edges. So it's a non-linear data structure consisting of nodes and edges. And why it is important is it can be used to represent various applications. Say for example, physical system interactions. So this is an example of physical system interaction. So you have different objects and how they move in relation to each other. This is something that is being widely used in computer vision because you have the object and it always moves in relation to other. If you have some physics thing like a spring mass system or even a video, you will be seeing that objects are always in relation to each other. So physical system interactions is one area where graphs can be used, and the second area is knowledge graphs actually. So knowledge graphs essentially picks out the important entities in the data and creates a graph with it. With it, we can be exploring the data, we can be mining the data, and it's also one of the most used things in web search nowadays. And the third thing, and this is the one of the most widely used things, which is the molecular interaction. So here, if you see, this is a molecule. So this molecule has a huge structure, and each of the element comprised of the nodes actually. The oxygen and hydrogen forms the nodes, and the bond they may make form the edges. So when you try to represent the molecules in this particular format, you could be able to understand how they interact with each other. So this is another important area where the graphs can be used. The next thing is the transportation routes. So even the here, if you see transportation routes essentially has various stops and how you transport through them. So each stop can be represented as a node, and the pathway can be represented as the edges. So in this way, even the transportation routes can be represented with the help of a graph. And information interaction. Information interaction is similar to knowledge graphs, where you can use the paragraph to form a meaningful representation. So graph is a non-Euclidean data actually. If you consider something like a image in computer vision, it can be represented in the Euclidean space with XY axis, say. Even NLP, if you consider the sentences, they can be represented in a Euclidean space. They could have a specific meaning because they are in a, for example, the similarity, you will be seeing that sentence similarity or a word similarity. If two things are near to each other, they would have a similar meaning. So images and languages works on Euclidean space, but why graph is something that's very different is it is being used in non-Euclidean space. So these nodes and edges, they can be represented in a Euclidean space, and these have meaning only because they are connected with other entities. So that's why graph is both an interesting and challenging subject in the deep learning area. So why is there a need for GCN? GCN is essentially graph convolutional network. So the neural networks, essentially, why it is difficult for graphs is graphs usually in the real life data are huge. They have thousands of nodes and millions of edges. So if you pass one graph in a single iteration to the neural network, it's the computation is very huge, and the training is not at all effective. So how do you train those graphs, and how do you represent this non-Euclidean space into Euclidean space? So these are some of the challenges that we face while training a graph in a neural network. And one of the most popular neural network used for graphs is graph convolution network. So how is the graph convolution network useful? It helps in finding the local patterns seen in the graphs. So let's say we take a straight chain molecule and we take a cyclic molecule. So these have specific structures. So these structures can be represented and found with the help of neural networks. And recognizing the hierarchies in the patterns is also very important. And also, finding the local patterns irrespective of the variation of the space. So finding this pattern, and let's say that there is a larger straight chain. So these are essentially the same pattern. It's a straight chain. So for finding the patterns irrespective of the size in which they occur. So that is also an important thing that we must be understanding. And graphs essentially can be greatly benefited from stacking the convolutional layers. So due to these various reasons, graph convolutional networks can be used to find how a graph is being represented. And today's session we'll be seeing how we could be able to classify the graphs. We would classify graphs in two ways actually. We would classify either as each individual node, how to classify it, or as a graph as a whole, how to classify it. So there are two approaches in which it could be proceeded with. We will be seeing how each node could be classified with in this particular session. So here if you see, so this is a single graph. So one of the widely used ways in graphs is the social network or the citation networks. So we have various social networking sites. Let's say, for example, Facebook or LinkedIn. That the friends essentially represent the each of our friends represents a node, and how we are. Let's say I am the user here, and I am linked to the friend 1, friend 2, and friend 3, and they could be connected in many ways. So let's say, for example, there is a node, and two of my friends are connected to this. So what GCN would help me to do is find this pattern and tell. So this node could be someone I knew, and give this node, the new user, as a suggestion to me. So that's how in social networks and citation networks it's hugely helpful. The GCN is, and it could be predicted. The prediction could be made here. So here if we take, so this is the original network. So each of the nodes would be the users, and what we are essentially obtaining with GCN is we are creating this into bringing this into a embedding space. So here if we see, so let's take these two nodes, U and V. So the U has been represented here, and V has been represented here. Let's say, for example, all these nodes are represented here, and this particular node is represented here. So when you represent in a Euclidean space at the embedding space, what you can do is you can bring in classical ML, like a classification, and classify the nodes. So here if you see, I have classified it. The upper nodes represent a different class A, and the lower space represents class B. So this way we could be classifying each node with the help of GCN. So here, instead of as a single graph and for finding individual nodes, in this particular case of GCN, what we are doing is we are giving a whole graph actually. So here, if you see, this is an invoice graph. So we have an invoice. So invoice, why it is a challenging thing to represent is, invoice could be arranged in whichever way. So here, if you see that there will be items, there will be a taxes, and what those taxes and the individual item cost are, and what is the total. So this will be the overall representation of an invoice, but it could have different representation. Let's say, for example, here it is in the upper right, let's say for example, and there could be another invoice where it is in the bottommost section. So even though this has a pattern, it could be anywhere inside this page. It could be here, it could be here, it could be here, it could be here. So to correctly extract those information becomes a very difficult thing, and GCN comes to the rescue, because here what we do in GCN is we consider each of these entities as a separate node, and we see what those nodes are connected in relation with each other. So here, if you see, the total is connected with the taxes and this amount. So essentially, when we try to find the representation, irrespective of the spatial position they are in, we will be able to find that with the total, the linking here would be the total amount that has cost. So in this way, irrespective of the spatial representation, we'll be able to extract the information we want from this, and that's why this is one of the widely used techniques in extracting invoices. So similar to the invoices that we saw in the previous slide, here what we see is the ID card digitalization. So here too, it's very similar. The challenge is very similar. So you have an ID card and you have different entities here, and they could be aligned in whatever ways. Every ID card will have a different alignment, and the photo could be here and the photo could be here. So those alignments, irrespective of those alignments, we should be able to extract those entities. So that is the challenge. So, and also okay, so irrespective of the alignment, we need to be able to extract those things. So here, if you, for example, let's say some of the personal details are here and the photo is here. There is a ID card too, where the photo is here and the personal details are here, but they will always have the counted entities in a specific pattern, and by exploiting the use of GCN, we will be able to create into the graph and extract those information. So that's why GCN is very helpful. So GCN is essentially one of the types of GCN is the message passing neural network. So this is a very famous technique, the message passing. So what happens here is at each layer, the future matrix, it is being aggregated using the propagation rule. So in this way, the futures become increasingly abstract. So let's say, for example, there is a node, there are another 3 nodes. So the message passing, what it does is it helps in aggregating this information. So once you aggregate this information and update this node with respect to the neighboring nodes, it gets better represented, and it's easier to classify it in relation to the nodes they are connected it. So that's what the message passing is all about. So how do you do the message passing? There are different propagation rules with which this message passing can be done, and the basic equation that helps in message passing is you take the representation of the node. Let's take, for example, this is the first node, this is the second node, this is the third node, and this is the fourth node. So the first node representation, how it could be updated is you take that representation and multiply with the weight matrix, and you add it with the weight matrix with the neighboring nodes representation. So this neighboring nodes representation you need to sum up. So let's say the nodes here that are counted as 2, 3, and 4. So those are being summed up to get this particular representation. And you average it. So there are three things. So there are three counting things. So the n will be 3. So by 3 would be the thing. So you average that thing and you add a bias. And after that, you multiply with the activation function. And once you apply this whole equation, what happens is this first node is updated with new information. And it essentially means that now it has information representing the 2, 3, 4, 2 with the help of this equation. So that's how each of the nodes is updated. And this is being done parallelly so that all the nodes have aggregated information. So if let's say, for example, this is the first layer. This is the first layer of the GCN where the aggregation happens. In the second layer, what happens is, so this 2 could be counted with some other nodes, and 2, 3, and 4 all could be counted with some other nodes. Again, you do aggregation. So at the second layer of GCN, this information will be aggregated and embedded in this future representation of the first node. So when you start the layers, more and more information of the graph structure is being embedded into that particular node, and this in turn helps in classifying the nodes. So that is what is the main idea with respect to the message passing neural networks. So you have a graph. So how do you aggregate this information? So I will just say what are the concepts that are there and how do you propagate this information throughout the graph. So the first idea that comes into picture is adjacency matrix. So adjacency matrix is essentially a square matrix to represent the finite graph. So each of the nodes, what it does it represents how they are counted with. Let's say, for example, the 0. 0 is counted with 1 and 2. So this is the 0 and it's counted with 1 and 2. So you get a 1, 1. And it's here in the adjacency matrix in the basic form, we don't take 0, it's not counted to 0. So we put a 0, and 0 is not counted to 3. So we put a 0. So you create a adjacency matrix. How in this sense is you can take each node and say how they are counted with other nodes. So once you create it iteratively, you see that so one is not count one. So here how it is counted with, and in this particular case, what they are taking is directed graph actually. So the graph actually, let's say for example, let's say 0, 1. This is the 1. So these two are being connected. So if you take this thing, it's an undirected graph. Let's take for example 0, and let's take for example 1, and we have a connection. So this is a directed graph with 0 getting directed towards 1. Depending upon our application, it could either be a undirected graph or it could be a directed graph. So in this particular case, this is a directed graph actually. So if you see, 3 is being connected to 1. So 3 is being connected to 1. So 3 is being connected to 1. So you put the value of 1 here, but 1 is not connected to 3. The arrow is this side. So the 1 is not connected to 3. So you have a 0. So depending upon the directed or undirected graph, you have ones and zeros, and then in turn the adjacency matrix will be different. So once you get this adjacency matrix, it's a one-way connection. Yeah, it's a directed connection. So 0 and 1, it's a undirected connection. Here you could say that 0 is connected to 1 and 1 is connected to 0. When you say a graph is directed, so it points in one direction. So that's why this adjacency matrix, here this representation of adjacency matrix is directed. When you create for an undirected, this value should change accordingly. So that is the idea behind here. So once you have this idea of adjacency matrix, the second idea that we will be bringing to picture is degree of the matrix. So
Now,
degree of the
Gautam, one question on that, the previous
yeah.
one. So before graph is processed by neural network, it need to be converted to adjacency matrix, correct?
Yeah.
But graph is propagating forward in a neural network. So in every node, it will be converted to adjacency matrix every time.
Let's say, for example, this is the propagation. The propagation here is little different from that of a conventional neural network, where here it will have a simultaneous updation. So what happens is you have a future. So 0, 1, 2, 3 would have each will have a futures. 0, 1, 2, and 3 will each have a future. So what we are trying to do with the adjacency matrix and degree matrix is we are essentially multiplying those two and creating an aggregation. So as said in the previous slides, so let's say for example 0, we are multiplying. Why we are multiplying with the adjacency and degree matrices? We are trying to aggregate 0 with the information of 1 and 2. So this is the first concept. So now we have established a matrix which has the connections. Again, the degree, we will know how much, what is the degree in which each node is connected. And I'll come up in the upcoming slides where the future adjacency and the degree will be multiplied in a way in which you could be representing the futures. Essentially, what the GCN, what it should do is we should aggregate this information. Let's say, for example, this node is there. We should aggregate the information from the neighboring nodes and update its information. To update its information, the things that we need is the adjacency and the degree matrix. Yeah, the graph with the help of the adjacency matrix and the degree matrix, you will be able to update. So how and why I will be telling in the upcoming slides. So adjacency is essentially the connections that are there. So what is degree? Degree matrix is essentially the diagonal matrix which contains the degree of each vertex actually. So here if you see, this is the graph, and if you take for example 1, it is being connected to 2, 3 and 5. So there is a tree. So each of the nodes, for example 2 is connected to 1 and 3. So there is a 2. So each node, what is the degree is being calculated, and hence the degree matrix is being obtained. So we have an adjacency matrix and we have a degree matrix. So once we have this adjacency and degree matrix, what we can do is we can tell how do we propagate the information. So propagation rules. So two of the propagation rules that we'll be seeing today is, the first one is the sum rule. The sum rule, what it does is contribution from each of the neighbors is being determined with the adjacency matrix. So adjacency into the future and summing out of. So I will be telling with an example how it is being done. So degree matrix is that for both the directed and undirected graph. So in undirected, whatever is the if there is a connection, we will take that as a degree. So in undirected, in directed, which is the incoming, that will only be taken as a degree. So that's the difference. So here if you see, so how this aggregation has been done. Let's take for example, there is a simple example I just tell. So there is this 0, this 1, 2 and 3. These are the incoming things. So how the adjacency matrix would be is 0, 0, 1, 2 and 3. So essentially how the adjacency matrix would be is 0 is not connected to 0, 0 is connected to 1, 2 and 3. So this is the adjacency matrix. Let's take for example a future representation of each of these nodes. The future representation, let it be whatever the number, the node ID, that is the future representation. So the future representation would be 0, 1, 2 and 3. So adjacency matrix would be multiplied with the future matrix, and what we'll be getting is 1 plus 2 plus 3. So essentially this is the 5, 6. So what our objective is, we need to aggregate the information 1 plus 2 plus 3. So essentially that is what this matrices are doing. The adjacency with a multiplying with the future matrix, you get the aggregation. So that's how the sum rule works. I hope you guys are clear, and I'll move on to the next slide. So now we have seen that we could be successfully doing the aggregation. Let's say, for example, what we saw was there was a 0, there was 1, and there was 2 and 3. We successfully aggregated all the nodes information to have this node. But there are two challenges. The first challenge is we are not aggregating its own information. So we need to create a self loop actually to aggregate its own information. So here if you see, in addition to the neighboring nodes, you have to create a self loop so that the node's own information is being aggregated. So that is one thing that we need to be changing. The next thing that we need to be doing is we need to in a lot of number of cases, what we need to be doing is finding it. Aggregation, mean aggregation is what our objective would be. Why mean aggregation is, let's take one is 100 and one is 2 and one is 3. So when you do a aggregation, it just tells 105. So you need to be dividing by the degree. So how much degree to have a better representation of that particular node. So that's where the degree of the matrix comes into the picture, because essentially after the sum you could do a mean rule actually. So this is the mean rule. So mean rule, what we are doing is we are having the features of each particular node. We are multiplying with the adjacency matrix, and we are dividing by the degree matrix. So once we do that, what we will be getting is, and here what happens is in the adjacency matrix, this particular adjacency matrix, what it does is it adds adjacency plus identity. So once you add both of these things, it will automatically take into the picture its own features. So that is the first thing. And because we are multiplying with the degree matrix, we will be taking care of the mean. So once you have this particular representation, you will be able to aggregate the mean representation for each particular node. So that is the idea behind the mean propagation. So we saw that we could be able to propagate with the help of the adjacency matrix and a degree matrix. So how do you do a classification? So for a classification, the first thing that we've been needing to do is we have a data. So what we need to do is we need to create into the graph first. So once we have the graph, we also need to have some idea of what are the nodes are, and let's say for example it should be classified as 1 or 2. So let's take here there are 10 nodes. We need to have at least 1 or 2 nodes which we know what is the labeling. Let's take for example this is the 1 node and this is the 2 node. We have just this information. So what we'll be doing is we'll be propagating this to a graph convolution network and back propagating the loss actually with respect to these 2 nodes alone. So when you back propagate with respect to these 2 nodes, all the other nodes will be updated. And here, if you see in the final thing, all the other nodes are updated with just these 2 nodes information. Because we are using 1 or 2 nodes in itself, it's a semi-supervised because we are using the information of a particular small quantity of nodes to get a representation of all the nodes in the graph. So that's why it's a semi-supervised classification. So I'll just give an idea of how the GCN works. First, what we do is we do a forward propagation. We have the feature matrix, we have the adjacency degree, we multiply it and classify it and check whether the classified node and the labeled node are same. If not the same, we back propagate the loss, and once we back propagate the loss, the weight matrices are being updated, and once the weight matrices are updated, we could be able to get a clear picture of what the labels of the unlabeled nodes are, so that we'll be able to picturize those. So this is how the classification with respect to GCN works. So I'll also go to the code actually. So GCN, it could be done in a number of ways. The particular method that I'm choosing here is deep graph library. So deep graph library has a higher APIs with which I would be able to build this GCN. So I'm installing DGL, importing the libraries that is needed for the GCN. So once I have those, I first need to construct the graph. So one of the classic examples in terms of GCN is the Karate Club graph. So Karate Club, what it happens is in Karate Club, it's a so this is the example graph where there are different members. In 30s, there are members. So you have essentially 33 members. So each of these 33 members, based upon the friends they have, they are connected. So here, if you see, there is a source and a destination. So this 1, 2, 2. So these are the source, and destination is 0. So 1 and 0 is being connected. 2 and 0 is being connected. 2 and 1 is being connected. 3 and 0 is connected. So you give the information of who are connected to who else in this particular karate club. So that is the first thing that we'll be doing. So once we have this information, we can here, if you see, there is a U that is concatenating the source and destination, and there's a V that is concatenating the destination and source. Why we are doing this? Why we are doing it 2 times is because this is an undirected graph. So if you just you represent just with U, it will be working like a directed graph with source pointing to the destination. Because you specify the 2 times with source and destination and source, it becomes an undirected graph. So data representation. So here I have given an example of how the data representation is there with respect to a karate club graph. Can it be used for all data types? Is a question that is being asked. It can be used even with a computer vision. Each pixel could be considered as a node, and they could be solved with the help of graph. But the thing with the graphs is where it actually has a lot more potential. Let's say, for example, a social network or something like a biological molecular interaction. There, those type of data will have a great benefits due to using this GCN. Okay, so this is a pre-built classic example. So in the real life, we would be, let's take for example, a Facebook is there. The people at Facebook will be knowing that who your connections are. So with that, the graph is there. Even they don't need to actually create the graph. They use this data structure, which essentially has the graph structure. So they will be able to see our connections only in a graphical way actually. So in this particular example, this is a pre-built. So it's having a it's telling that these people are connected with these, and how do we go about in classifying those people. So this is the idea here. So we are having a karate club. We are having 34 people. So there are 34 members in the club and 156 edges. So the 156 edges represent the people who are friends with each other. So here, if you see, in this particular thing, we are trying to make a visual representation of how they are. And so here, what is the problem objective is, in these 34 people, there is a manager and there is an instructor, and both have a class, and they decide to start their own clubs. Actually, there is a club 1 and club 2. So our problem objective is to find out who will join which club actually. So how do we go about it? The thing is here, just go here, 0 and 33. So in this, there are 34 members. So 0 and 33 represent the manager and the instructor. So both form their own clubs. So based on the connections they have, we need to be predicting who will go to which club. So that is our problem objective here, and we'll be seeing how we could go about here. The first thing is the embedding vector. So we need to be creating a embedding vector that is that for each of the nodes. And here we are giving a random initialization actually. So with the dimension equal to 5, we are giving a representation for each of the nodes as this is an example. So here, if you see the, let's take for example, this is the, we are printing out the future for the number 2. So here, if you see, there is a 5-dimensional tensor that is being represented, and again we are seeing for 2 members, 10 and 11, the future representation. So this is randomly initialized. In real life cases, based on the application, the future representation can be better represented. For example, in social citation network, the paper's topic can be made as a future representation. So based on the needs and the particular case, we could make a future representation for each of these nodes. So we are using deep graph libraries, high built-in API, which is a GraphCon, to represent the GCN. So what it does is, so this is we need to always be creating a class for the graphical neural networks. In this case, it's a graph convolution network. So the first is a graph convolution network, and here you are taking the input features, which is this 5-dimensional representation vectors, and it will be giving a hidden size, and again the hidden size will be giving the number of classes. So that is one of the things that we'll be able to represent it. And so here the particular GCN that we are representing here is a 2-layer thing. We have an input, we have a input layer, hidden layer, and an output layer. In the input layer, the representation of each of the nodes is a 5D. The hidden layer it's a 5D, and the output layer it's a 2D. So 2D representation. So here, if you see, this is the first layer. We are giving input features and we are getting the hidden features. This is the second layer where we are getting the hidden features and we are getting the number of classes. So this is the interpretation. And how do we, the forward propagation, we are specifying here. So with the inputs, we are getting it, and we are using a ReLU function. And after that, again, we are using it for the contour for the output. So we are defining the GCN class. Once we have defined this GCN class, we are getting the model. So this. So here in this particular code, what we are doing is, so we know the two people. So it's a semi-supervised. So in the whole group of 34 people, we know two people and their classes. So let's take this 0 as the inspector and 33 is the manager. The inspector has a 0 as a club and the 33 has 1 as the label. So we have the nodes and their labels. So once we have the nodes and labels, here it's in this particular code will be very similar to conventional neural network. How we are doing? We are defining an optimizer. We are recording the logics. We are recording the logics because we need to. In the end, you will be seeing a visual representation. For that, we are recording the logics actually. So after the ReLU layer, so this is the first layer. We are after the first from input to hidden, we are creating a con layer, and after that a ReLU, and after the ReLU we are from there we need to pass on to the hidden to output. So that's why this particular code exists. So these are the things, all logics we are recording because for the visual purposes. So we are defining a epoch of 50 actually. So here we are doing is the net and the graph and the inputs, the labeled nodes. So these things we are giving as inputs, and we are recording the logics for each of the nodes in each of the epoch. So we are appending with all logics, and here we are doing a softmax, and here we are checking with the labels that we have. For the 0 and 33, we have a 0 and 1. What is the labels that this gives? And we are back propagating the loss and stepping up the optimizer. This is the PyTorch optimizer syntax, and we are seeing how much the loss is actually. So how much is the loss actually? So here if you see, we have given a 50 epochs actually. So if in the 50 epochs, it keeps on decreasing. The loss was 1.44, and here if you see as the epochs increases, it keeps on decreasing, and at the 50th epoch, it's actually 0.40. So it's essentially decreasing. And here what we're doing is essentially in each of the epochs how the node has been updated, that we need to have a visual representation. So that we are trying here. We are defining the colors, and we are creating the axis, the representation, the figure. And here if you see, so here is the at the 0 epoch, all the numbers are in a particular let's say for example they represent 0. So once the epochs keeps increasing, what happens is each of the node will be better represented, and they will be moving to a different section. So you will be getting a better representation of who belongs to the club of 0 and who belongs to the club of 1. So once you know this information, the classification is being done, and now you'll be knowing this has a good accuracy of 80%. So you'll be knowing the 80% accuracy who will be going to the club 1 and who will be going to the club 2. So this is how you do a classification with respect to graphs. And yeah, this is the thing, guys. If you have any doubts, please do ask.
Okay, that animation is cool, by the way. Good session. So audience, any questions?
Transfer learning within graphs, I haven't seen much actually up to now. I'm not sure whether we would be able to do a transfer learning in graphs actually.
Yeah, that's a good question, Gautama. So in traditional computer vision and NLP, we have these pre-trained models. In graph also, will we have pre-trained models?
No, as of now, I haven't seen any pre-trained models.
Okay, let's say I train a graph on a pre-trained model on graph using Wikipedia, which is all of most of the global text, right? So I can use a pre-trained graph model on Wikipedia for NLP text, and then with that pre-trained model, I can probably do some data mining on incremental text samples. Maybe, not sure. So maybe
Not
it is
sure,
a future innovation. So
and also the graph, one of the main things is it has a meaning because it's connected with those nodes. When it becomes another graph, it's altogether a different entity. I'm not sure whether it will be working.
There are some additional questions here.
Yeah. So recommended papers.
Questions.
Yeah. So recommended papers. It would be good to start with semi-supervised classification. There is a famous paper. Even in my paper, I have made a link to it. And there are not many books on graphs. It's an upcoming area. Two of the most used libraries are PyTorch geometric and deep graph libraries. And here you would find some good examples for graphs.
I have shared this graph paper which Gautaman has written. So all of you just got it now. It is a Google Drive link. You can download it. So both quantum ML paper and this graph paper has been shared via chat here. There are some additional questions, Gautaman.
Yeah. So the relation between entities be predefined. Here it is predefined. Here the karate club, you have the predefined thing of who they are connected with. It is not essentially in every case it should be predefined. For example, in the case of the invoice extraction, if you need to be training in such a way that even if you give a new invoice that has a different spatial orientation, you should be able to extract those information. And also the next question, by using what information it is being divided into the two classes actually. So it's based on how much connections it has with. We have two labeled nodes, 0 and 33. So how it is classifying is how much connections the 0 and 33 has with that particular node. Let's take, for example, there is a node pi that has connections with lot of members who in turn has connections with 0. So essentially, it means that he is more aligned towards 0 actually. So that's how, based upon the connections and the affinity, it's really classifying those nodes. And the deal framework that both PyTorch and MXNet are being widely used in graphs. Here in this particular case, PyTorch is being used.
Okay, so any final question, audience, before we go to our next session? Okay, so paper has been shared via chat, and thank you, Gautaman, excellent session. And let me go to the next session for today. Next, we have Bismillah Kani with the chest X-ray analyzer, which is a kind of experience report paper. Gautaman, you're saying something?
Yeah, thanks, Vivek, and thanks, guys, for attending this session.
Thank you, Gautaman. Excellent session indeed, and look forward to your future graph webinars as well. So paper has been provided. Thanks once again. So let me now make Bismillah as presenter. Bismillah, good afternoon. Bismillah, how is it going?
Okay. Hello all, good afternoon and welcome to today's presentation. My name is Bismillah Kane. I'm an AI researcher in CellStrat AI lab. Today I will be presenting you all about the chest X-ray analyzer tool that we developed for diagnosing the COVID-19 disease. So today the content of the presentation is as follows. First, we'll start with the introduction to the tool, and then I will give you a brief explanation about the building blocks of the tool, and then I will explain you each modules of the building blocks, namely the disease prediction module, and then the model visualization module, and finally I'll make a conclusion of our tool, and also will give you a live demo of the tool usage. As you all are aware of, now we are in a COVID-19 pandemic situation, and this is an unprecedented healthcare challenge that has been faced globally. It has created a huge healthcare crisis, and the healthcare systems are being overwhelmed by the situation that's created by the COVID-19 pandemic. So in this situation, as the number of cases have been increasing globally, so the main challenge for the healthcare system is to how efficiently we can screen the patients, how efficiently we can test the patients if a particular person is COVID positive or negative. Currently, the gold standard for testing the COVID-19 disease is the RT-PCR test. However, this test is time consuming and also expensive, and also it is not widespread, and the reach of this test is not to the level that we would expect in a country like India. So we clearly are in a healthcare crisis and we have to respond. And so from our AI team, we picked up this problem statement a couple of months back, and we started working on this chest X-ray analyzer tool, and we collected data set yeah, X-ray images related to COVID-19 disease. And then after we build a working model, then we go on to create an easy to access and easy to access and easy to use on online tool that we call it as chest X-ray analyzer tool. The main goal of this tool is that to provide an easy access to the healthcare professionals and also the public usage, so that they can use this tool for supportive aid to do a medical diagnostics. So this is under development. So this is no clinical trials have been done to validate this tool, but here we are providing you an prototype version of the tool. It's a working version. So this tool is being deployed in our website ai.cellstrat.com, and this is a screenshot of the tool. Currently it is being deployed.
Yeah,
So
so just to clarify that point, last point, it says not for medical use. So it is actually being launched for global medical community. But yes, it's a disclaimer that we do not have, clinical trials done on this or any kind of regulatory, oversight yet. So that's why we have a disclaimer. But indeed, it works quite accurately when we tested it, and we'll be launching it to the world in near future.
okay, thank you. Moving on, more detail about how this tool was built. So the tool essentially has three main modules. One is the disease prediction module, and then there is a model visualization module, and the third one is an out of distribution module, and each module has its own purpose. The disease prediction module, what it does is that it takes and chest x-ray images in input, and it uses a deep learning model, and it outputs the probabilities of the diseases. In our case, we have considered three diseases: COVID, pneumonia, and normal. But this tool can also be generalized as a general chest X-ray analyzer tool if we train it on a wider range of diseases with sufficient training image data. So that is disease prediction module, what it does. And the second module is the model visualization module. So what this module does is that it gives an visual explanation of how the disease prediction module made a prediction of a particular disease. So in most of the AI tools, what you do is you give an input as image and you get an output. In this case, the probability of disease. But in many cases, we miss to give an additional intuition of to the user who does not understand the nuances of the deep learnings and the working of it. So it will be really useful if you give an intuition by a visual explanation of which area the model looked into it. So we will see the details in coming slides. And the third module is also an important module, which is called as the out of distribution module. So imagine a situation that we now have a chest X-ray analyzer tool, but let's say the user goes and uploads an irrelevant images. Let's say he uploads an orthopedic of images from, let's say, hand X-ray or a brain CT scan. So you need to provide a module that detects such types of irrelevant images upload, and then intimate the users that hey, you are not uploading a relevant image, so I cannot do predictions. Yeah, currently this module is under development and we'll be integrating into the tool in the next release. So now we'll go into the each modules. Okay, so the first module is the disease prediction module. So this module works on transfer learning. So we used ResNet 34 as a CNN backbone architecture, and we created a custom head for fine tuning on our COVID-19 data set. Okay, so how do we fine tune is that we remove, so here is the ResNet 34. So we remove the last two fully connected layers of ResNet 34 and we replace them with a series of layers as shown in this head part of this CNN architecture. So it has an layer called ACP, which is called as an adaptive concatenated pooling layer. So this has been this has concatenation of max pooling as well as the global average pooling, because it has an advantage of having both global average pooling and max pooling concatenated, because for certain use case max pooling works better, for certain use case global average pooling works better. So when you combine both, then it kind of generalizes for all kind of problems. And then we do add a couple of layers, like a fully connected layer and followed by a batch normalization, dropout, and another linear layer. So this whole set here is shown is like it's added as a two sets. Okay, it's not like bn followed by a bn, but it's a bn then a dropout and then a fully connected. This whole set is then being added as two. Okay, And then the fully connected layer is being connected to an output layer, which is a softmax. Okay, and this softmax gives the probability of the three diseases. So this is a COVID, pneumonia, and normal. So then it outputs a probability. Let's say this is COVID, and then let's say this is uh, pneumonia, and then let's say this is this one. So then in this case, this is being labeled as COVID. Okay. So for training this architecture, we used training images from NIH dataset. Okay, it's a collection of 100K images, or more than 100K images, but it has about 14 diseases. Okay, and we picked two diseases. One is disease, but another is not a disease. So one is the pneumonia, another is a normal. And this NIH does not contains COVID-19 images, because COVID-19 is very recent. So the COVID-19 images are primarily taken from this repository. This repository was built by University of Montreal, led by Professor Joseph Paul Cohen. So he initiated to start this COVID chest X-ray dataset repository. It's a public repository, and to the knowledge that to the best of our knowledge, this is the only public data set that is available for COVID-19 images. And this is one of the main challenge that has been faced by AI researchers to build an AI tool, such as a chest X-ray analyzer tool for medical diagnostics of COVID-19 disease. There has been some initiatives taken by RSNA, so Radiology Society of North America. So they announced that they will develop the largest COVID-19 chest X-ray images, but that has not been released yet. So in future, we will be releasing the next version of our tool with trained on much larger data set, let's say RSNA data set. So moving on to our next module, which is the model visualization module. As I told you that an AI tool is mostly a black box for healthcare professionals or radiologists or any common users. So he does not understand why the model has predicted this particular chest X-ray to be a particular disease, let's say COVID. So to augment our model disease prediction module, we also added a model visualization module. So for that, we used a technique called GradCam. So it's a gradient class activation map visualization technique. So this provide a visualization of model on the concept that why they predict what they predict. So we will not go into the details of how the GradCam works. So there was a webinar that was given on GradCam previously. I encourage you to watch that video where we have explained in detail the workings of GradCam. But in summary, what GradCam does is that it produces a heat map visualization as shown in this picture here. Okay, and it highlights the regions of the images that the model looked. So for example, take this image, and when you create a GradCam heat map visualization, so it highlights these two regions of the lungs. So it says that it looked here to predict that this image to be a COVID. The GradCam just not only gives you an explanation of why it predict, but it also gives some extra intuition of whether your model is working correctly or not. So for example, the model also looked into this text, right? So probably that it might not be 100% correct that the model predicted this diseases, because it should not have looked here because it has a text here. So it also gives an extra debugging tool for the AI researchers to look into the working of your tool and then go and fine tune it. Yeah, so with that, I'm coming to the conclusion of this presentation. So what we have done is that we have a an complete working AI tool for COVID-19 disease predictions, which takes chest X-ray inputs as inputs and outputs the disease prediction. It not only also do the disease predictions, but it also gives you an extra visual explanation of the model. And the main challenge that still remains to be for AI researchers like us is that the availability of enough training data of COVID-19 chest X-ray images. Yes, there are some initiatives, but it is still not reached to the level. So with this tool, what we believe that we have provided an easy to access tool to healthcare professionals, so they can use it for screening of patients in a much faster and a better way. And we also like to engage with healthcare professionals through this tool and get feedback and help to bridge the gap between the healthcare systems and the AI researchers, and to provide a much better system for medical diagnostics using the AI technology. Yeah, with that I conclude my presentation, and these are the references I used. So with this I will go for demo, and before that I will see if there are some questions.
Yeah, I've shared the paper. Google Drive link has been shared in chat. So audience, you can download the PDF paper on this.
Okay. So
yeah, Bismillah, we can demo the product perhaps.
okay. Okay, so I'll go to our tool. So it is available in aa.cellstrat.com, and since I have already logged in, it's taking me to it. But in case if you are using it for the first time, it will ask you to set up an account, and once your account setting is setup is over, it will launch you into this home page. So here we have
You may want to
our
share your screen. Screen is not shared.
one minute.
Under sharing, you can click on show screen.
Okay, okay, it got stopped. Okay, so I'll continue. So are you able to see my screen? Can you confirm me?
Yes. Yes.
Okay. Okay, so I am at aa.cellstrat.com. So this is the home page, and here you can see links to our healthcare products. So today I am presenting you the chest X-ray analyzer tool, and if you click into it, it goes to this session. So yeah, this is the tool. So here it has the dashboard of the sessions you will be creating it, and this is the workspace session. So what you can do is you can start a session, okay, and here you can go and upload images. Let's say we upload these two images, and once you can click upload files. So this works. So yeah, and then click predict once it upload has been successful, and it starts the prediction. In the back end, it uses AWS endpoints. So the model, our AI model or the chest X-ray model has been deployed in AWS SageMaker endpoints, and then once you upload and start predict, it will invoke the AWS endpoints, and it will send the images to our S3 bucket in AWS, and our predict method calls the predict function, and it reads these images from S3, and it processes it and gives you the output, and it sends back the results to this web client. And now yes, you can see the results has been done, and you can view the results. And here you can see it has an indicator of what is the disease and what is the probability. So in this case, this is in COVID, and it has a probability of 100%. And in this case, this is a pneumonia, and it has a probability of 99%. And in addition to this, you can also visualize the heat map, as I told you, the model visualization module. And once it is you toggle this button, it produces a heat map, and it highlights the regions where the model looked into it. Yeah, you can try, you can aa.cellstrat.com, try, and please provide your feedback, positive or critical feedback for improvements. Yeah, with that, I conclude my presentation and also the demo. And if there are any questions, I can take it now.
I think there are one or two questions, and you may also want to just give a glance of the paper itself.
Okay, I do not see the questions anymore. Okay, so this is the paper that we are presenting today. So this is a little more detailed than the presentation, and abstraction of this paper, and introduction sections where we explain you about the tool, the motivation to build such tools, and what is um, key aspects of this tool, and what are the building blocks of this tool, which I explained you. There's a three modules, and what is the model architecture that we use to train or develop this model, and also some information, more information about the data. As I told you, the data is not enough, especially the COVID-19 images. And to overcome this gap, what we did is we used two techniques, data augmentation and oversampling. A snapshot of some of the data augmentation that we used in this research is shown here. In the top row, it is random rotation, so it is rotated to -30 to +30, and some brightness transform. So some of them is we actually validated with our healthcare experts, and asked him what makes sense, because these are some medical images, so you cannot be going wild with your data augmentation. So you have to be very careful in your data augmentation and do not go overboard with making it too dark as shown here, or too bright as is shown here, or completely rotating it to upside down. No, it cannot be possible. So you have to be aware of what data augmentation that you're doing it, and we have to be carefully selecting a subset of data augmentation possible. And so that is one technique that we use to overcome the lack of sufficient data. Another technique is the oversampling. So what does oversampling does is that since we have very less number of images for COVID-19, yeah, so what we did is we tried to balance this class distribution, because the normal image is having a huge number of images, and pneumonia is less, and COVID is very less. So we kind of give more weightage for COVID images and less weightage for normal images. So in that way, your model training will be generalized and it is not biased to the class which has a large number of images. That is one thing. Then about the model visualization, GradCam, which I already also explained, and conclusion. Yeah.
Okay, that's great. Audience, any questions? There's a question here. I don't know if you answered it. Instead of pre-trained model ResNet, can I use optimized or our own model? So is it possible to use custom model rather than pre-trained model like ResNet?
Yes, you can use, but since yeah, you can do experiment with different things, like let's say since you don't have sufficient data, especially with COVID-19 images, instead of starting or initializing your weights by random weights, probably it is better that you can use pre-trained weights and you can fine-tune it. That will be much that gives probably gives you much better accuracy.
Okay, so folks, any other questions for Bismillah?
Please share COVID test images to test it on. Yeah, you can also Google it, COVID-19 images, and probably I can share you this link. Where is this? Yeah. Where
Another
should I
idea to
paste
find
in the?
authentic images is you can search on stock photo sites like Getty Images or Shutterstock. If you search for COVID images, you'll find the authentic images and you can test with them.
Yeah, I send the link to the database.
Yeah.
You can download the images from that.
Okay, any other questions, audience? So, all right, so excellent presentation, Bismillah, as usual, and a very sleek and concise paper, very well presented. And this product is being launched next week, and we'll be doing a global announcement through our large community, which is 14,000 strong, and over social media channels. So we'll do a soft launch first to try to get some initial feedback from global healthcare providers. And we do understand that we will have to seek regulatory approval in different countries, such as USA FDA approval or Indian healthcare regulators as well. So that's fine. So that will be in due course. But yes, we'll be announcing a public launch of this platform with 3 products launched: COVID-19 chest X-ray analyzer, and CT scan segmentation, and diabetic retinopathy predictor. We also have this fantastic product team going on. If you are interested in joining our product team, just reach out to us offline. Thanks once again, Bismillah. Very well presented and very crisp session. So look forward to your future sessions as well. The paper
Yeah.
has been shared. Okay, so paper has been shared on the chat, and it will be available on our paper section in by tomorrow, hopefully. So all the 3 papers have been shared. So Bismillah, any final points?
No, thank you everyone for your attention. Yeah.
Thanks, Bismillah. Thanks once again. And audience, so with that, that concludes our morning session. We'll continue with the afternoon session.
Hello everyone. My name is Shubha and I am an AI researcher at CellStrat AI Lab with specialization in deep reinforcement learning. So today's topic is we will do a summary of the AlphaZero algorithm. So it was an algorithm developed by DeepMind to win against the game of Go. So as we proceed, I will give a brief intro on the game of Go and the different versions that were released by DeepMind and their algorithm. So let's get started over here. So basically, Go is an ancient Chinese game. It's very widely played in China and Korea. But then the difference between Go and chess is Go is very much more complicated compared to chess. So as you can see, the standard board size of the Go game is 19 cross 19. The game is something like this. I will just tell it approximately that you have black coins and white coins, and then each person should try to enclose spaces. So if they can form enclosed spaces, then if suppose white is able to enclose one particular space, then he gets to take away all the black coins within that enclosed space. So basically, they try to form as many enclosed spaces as possible, though this is not the complete list of all the rules of the game. This is just an idea of what exactly that game is. You all know that in sometime in 97, IBM came up with this algorithm which defeated the world's best champion in the game of chess. But then Go was never possible till recently because Go was much, much more complicated. So in 2016, this DeepMind, though it was initially a startup by itself, by 2016, Google had acquired it. And so Google DeepMind in 2016, they came up with a way to build a program which is able to achieve superhuman performance in the game of Go. And they tested it on the world champion Lee Sedol in Korea, and then they were able to defeat the world champion in this game of Go. After that, after 2016, sometime in 2017, they came up with the advanced version of what they delivered earlier, and we will see what are those advanced versions. So with this brief introduction on what exactly is the game and what is the program that we are trying to discuss, let's just get in. In 2016, they came up with this program AlphaGo. So what happened with AlphaGo is AlphaGo learned by looking at expert moves. So basically what you need for this, you need an expert to play the game of Go, and you capture all the expert moves and frame it into a data set. And this data set is passed to your neural network, and the program learned how to master the game of Go. So the disadvantage with this was it is limited to what an expert can play. So it is just human level performance. The best expert that any human can play, it is just human level performance, and it was limited to that. Though they played with this person, world champion Lee Sedol in Seoul, Korea, the program won only 4 times. It was a 5-game quiz test that was going on, but then it was able to win only 4 times. So one time Lee Sedol was able to win against this program. However, in 2017, they came up with this program AlphaGo Zero, wherein it learned by itself. That is, it did not need any kind of expert moves or uh, expert configurations and create a data set and feed it to the neural network. So what happened is it played against itself. It played multiple times. The same neural network was played against itself, and hence it learned by playing with itself, and then it learned how to master the game of Go. Hence The title of this summary is Trying to Master the Game of Go Tabula Rasa. So from the scratch, using self-play, that is, it played against itself and it was able to master the game. And this second particular version was able to beat the first version, which is AlphaGo. 100:0. So they played it 100 times against the first version, and all 100 times the second version was able to win. And the third one, sometime just 2 months later, they came up with AlphaZero, where they were able to extend this to all kind of classical games. So chess, shogi is a Japanese game which is similar to chess. So all these kind of classical games, they just generalized it for all such games, and hence they removed the name Go from the title. So what do you mean by classical games? When I refer to classical games over here, it means that the games which you play, which are based on the skill, which are based on skills exhibited by the players. So if you think of chess or Go, it solely depends upon your own skill, your own intellect on how well you can play, compared to games like maybe rock paper scissors or monopoly, or if you're trying to play some dice game or something like that, it is not based on skill, it is based on luck. There is an element of luck within that. So this algorithm can be applied to any of the classic games. So we can also do this for if you can implement this algorithm for simpler things like either tic-tac-toe or connect 4, wherein you can just copy the simple program, because if you want to train it for Go, it's going to be really tough. So if you can just get the hang of understanding of this algorithm by trying it out for simpler games. So what are the different components that formed this particular algorithm? You have something called as a Monte Carlo tree search. Monte Carlo tree search is a tree search algorithm that was designed sometime in 2006. So they designed this algorithm specifically to use for games such as Go. So basically, when there are games which have a very high or enormous branching factor, you use something called as Monte Carlo tree search. You represent the game in terms of Monte Carlo tree search, and then you can solve it. But then, though they figured out this and they were able to represent the game as an MCTS, they did not have the computation power to write a program to achieve superhuman performance. So as with DQ and beating Atari games, deep learning was the key thing in order to able to get this in able to achieve this feat. So basically the neural network architecture is, they have a two-headed neural network which is of actor critic style, which we have seen in reinforcement learning. This actor critic neural network was combined with Monte Carlo tree search, which is basically the entire program. So basically, this neural network is a residual CNN, because uh, the game was passed to the neural network as images. The images of different board positions are taken. So there could be different configurations, right? So if that is your board, then there could be a configuration of there is a white pawn, there is a black pawn, and so on. So every configuration is taken in as an image and passed as input to the neural network. And so to read the images, a residual CNN was built in the actor critic style. So as we know that the actor critic has two different heads. One is the policy head and the value head. Policy gives out a policy on what particular next action has to be, and the value head evaluates how good was that action. So this neural network guided your Monte Carlo tree search, which helped them to build this program. So a quick introduction of what is Monte Carlo tree search. There is something called as game tree concepts, where games are modeled as trees. So this is kind of simple. So you can model this game of tic-tac-toe as a tree. You start from the root node. This will be your root node, and from the root node you will have different actions possible. So these are the different actions possible. You can take any of those actions. And once you take any of those actions, the opponent can make a different action, and then you can make different action, and so on the tree goes. So if you are able to represent any game in this particular format, it is a game tree. So a quick introduction: the node represents the state and edge represents your action, and on performing your action there is a transition from the node to the child, and terminal nodes are the leaf nodes. So once you win or lose the game, or there is a draw, you get to a terminal node. That terminal node becomes the leaf node. So just imagine that you, as I told, Go is a 19x19 board. Just imagine that you have represented Go or chess as this particular tree. So a brute force search would be to try out all the different paths in order to determine which move results in winning. So if you're at one particular point, then then suppose say you're at the root, then you need to say which move if you make from this particular point will it lead to a win. So if you have to figure this out using brute force approach for chess or Go, even for tic-tac-toe for that matter, it is going to be very tough and impossible. Which is why we have this Monte Carlo tree search algorithm, which we will just see how exactly does selection happen over there. So Monte Carlo tree search follows 4 different steps. The first one is the selection, and then you have expansion, then you have simulation, and finally backpropagation. So from the root node, let's say that you're starting from scratch. So you start from the root node. You need to make a selection of one of the children. How exactly do we make this selection? I'll come to this in the next slide. Based on one particular formula, you make a selection. After you select that particular node, you expand it. That is, from that node, you randomly pick one unvisited child. So expansion is to pick one unvisited child from the node that was selected. Simulation is from that unvisited child, make a random simulation. So expansion is, this was the node. So from this node, one random unvisited child was taken. And from that child, you have to make a simulation. Simulation would be move till the end or move till the terminal point. And once you move to the terminal point, you will know whether you have won or lost, and that result is back propagated all the way till the root. So these are the basic 4 steps of your Monte Carlo tree search. But then in the first step, I told you that you have to make a selection. So let's quickly see how that selection is possible. There is this formula called as UCB, or upper confidence bound. So this is a formula which helps you make a particular choice. This is derived from the bandit algorithm. So in bandit algorithm is a single state algorithm. So basically in casinos, if you have to pull levers, there are several levers. Let's say that there are 5 levers. You have to pull a particular lever, and if you are lucky enough to pull the best lever, then you are rewarded very highly. If you pull any other levers, you are rewarded a bit low, and the worst lever could give you a 0 reward. So this is basically a single state. There is just one state and you have to choose 5 different actions. So this is your bandit algorithm. And how exactly do you pull a particular lever is guided by this formula. So in bandit algorithm, the formula is different, but then for Monte Carlo tree search, it is guided by this formula. So I just gave an analogy. So which node to select is given by this. Let's quickly go through that. WI is the number of simulations which resulted in a win. So if you want to choose a particular node, it will give you the number of wins, which means how many times previously did you choose this node which resulted in a win, and the total number of simulations that you made. So you visited this node, how many total times did you visit this particular node is given by S of I, and how many times did you visit this particular node which resulted in a win is given by W of I. And C is a hyperparameter, exploration parameter. And then the second term comprises of SP and SI. SI is same as this, so total number of times that particular node was visited, and SP is total number of times the parent was visited. So if you look at this particular equation, this becomes your exploitation criteria, and this becomes your exploration criteria. So you are selecting a node based on these two things. This helps you exploit the knowledge that you already know, which means you are choosing a node. So how many times did you win by choosing that node? So if this is really very high, you would want to exploit the information that you have already figured out. And if this is okay, not that high, this leads to your exploration, which is how many times did you actually visit that particular node. So if you have not visited that node too many number of times, then if you have not even visited it even once, then it is time to visit it to explore what exactly is happening. So basically, this is the formula for selecting a particular node. I'll quickly go back. The first step selection is based on the formula which you just saw. So you select a node, you expand, that is, you go to some unvisited node, you simulate all the way till the end, and based on that, the result that you get is back propagated all the way till your root node. So that was a very brief introduction about what is Monte Carlo research. Now we will have to see how that is integrated with your actor-critic approach.
So Shubha, these
So
are
in
two
AlphaGo,
different things, right? So
yes,
you
yes.
are
So
MCTS is a sort of an independent technique, and now you are saying we will merge it with a
correct,
reinforcement learning algo called Alpha Zero.
correct,
Okay.
correct. So if you can just build that MCTS for AlphaZero, still you will not be able to compute. You can only do it with the, because MCTS was introduced way back in 2006. They developed it specifically for the game of Go. But then still they were not able to build a program which could achieve superhuman performance. But now with integration of actor critic with that, that is moving back and forth, where this neural network basically guides how to build the tree, and once finally you finish the training and the entire tree is built, you can use that tree to play new games. So that tree will tell you which is the best action to take at every given step. So that is how it works. Yeah, so one quick question. What if SI is 0? Yeah, in this formula, yes, but then they do add a 1 over here. In many formulas, there are different versions of the same formula. So they just do add a 1 over here to make sure that SI doesn't go to 0. Let's look at how policy iteration. So it works based on policy iteration. Policy iteration is something we have seen in dynamic programming. So what exactly is policy iteration is, you take some random policy, and you evaluate this policy. And once you evaluate and you've seen the results, you improve it. And after you improve it, you get an improvised policy pi dash. Now you evaluate the policy pi dash and again try to improve it. So the sequence of things where you evaluate a policy and improve it, evaluate it and improve it, is the process of policy iteration and dynamic programming. So AlphaZero is using a neural network to guide your Monte Carlo research. And basically policies iteration is used to train this neural network. So the neural network, the actor part of the neural network, just gives you a policy and you evaluate it and you improve it. So you iterate over that procedure to improve your neural network. And policy iteration is your classic algorithm which generates a series of improving policy by alternating between policy evaluation and policy improvement. So policy improvement is nothing but evaluate your value function for the current policy. So alpha 0 is can be understood as a simple policy iteration where MCTS is used for both policy improvement and policy evaluation. In the coming slides, we'll quickly see how they're integrated together. So as I said before, it starts with a random policy. It executes a Monte Carlo tree search based on this random policy, based on the policy's recommendation, and the Monte Carlo tree search projects a more improved, stronger policy back to the neural network. The neural network calculates a loss function by considering the policy that it has and the policy which was given out by the Monte Carlo tree search, and it trains itself. So policy evaluation is applied to the much stronger search policies, and the outcomes of self-play games are also projected back to the function space of your neural network.
So in a way, you can say both the algorithms are like breathing algorithms, and so they toggle and they try to improve each other.
Yes, that's right.
So in a way, they are giving feedback to each other to improve the other party, and so neural network trains and tries to improve itself based on MCTS feedback, and based on neural network, MCTS develops further hypothesis.
That's right.
Right?
That's right. Yes,
Okay.
that's right. So what Vivek told is basically been summarized over here. You first have a deep neural network f of theta, which has parameters theta, and this is an actor critic network. So basically, so your f of theta is supposed to give you probability and value. This is actor, this is critic. It has two heads. One head gives out the policy. Policy is nothing but probability over actions. Value is nothing but your critic. It tells you how good was that policy. So that is actor critic algorithm, and your neural network gives that output. And so probability is nothing but, as I told, what is the probability that is given out by the neural network? The policy actor part of it gives out the probability of taking an action in a particular state. So basically, if this is your neural network, if that is your Monte Carlo tree search, you are in the root, you are supposed to take an action. What is the action that you take? So it gives out that probability. Given a state, what is the action that you're supposed to take is given to you by the policy. And value is basically the probability of the current player winning from the position. So it tells you that if you take this particular, if you go via this path, what is the value of you winning? So this is a value between in the range -1 to 1. So if it says 0.8, then it means that you have an 80% chance of winning if you go via this path. If it is -0.9, then you have a 90% chance of losing if you go via this path. So the value head of your neural network evaluates the action. If it gives out a policy or an action that is supposed to take, value is evaluating that. So the neural network combines this into a single architecture, which is actor critic architecture. That is, you have a common body. Basically, if this is your neural network, you have a common body, but then later on it breaks down. So this could be your neural network, and then it breaks. This could be your actor, and that could be your critic. So it breaks in the end to have two different things. And this first part of it was built based on CNN. It used residual blocks of CNN because images were passed as input. So you need the configuration, right? So that configuration that is passed to the neural network were images, and hence the initial part of the neural network were CNNs. This is basically the same what was explained over there. So we need to see the formula for selection. So the formula for selection is slightly modified over here, so that the formula for selection has been slightly modified over here compared to the previous formula that you saw. So here you have the Q value that is basically the output value that was given out by the critic part of the neural network. You have an exploration parameter. So that, as I told, this is your exploitation and this is your exploration. So this hyperparameter is to control the degree of exploration that you want. And of course you have a probability, because this is multiplied by probability. So the probability of choosing an action multiplied by the next term. This is the number of times the parent has been visited, and this is the number of times the child has been visited. So instead of using the win rate, the Q value from the neural network is being used over here. So let's see how exactly the training happens. What you do is you initially have a neural network. The neural network gives you value for Q and the probability. So based on the maximum value of Q plus U, you just choose a particular action and you go on. You do this selection, and after selection you expand and move all the way till the end. You do not simulate like we saw previously. You do not simulate till the end, but then the value that you got from your neural network is back propagated. So once you build this tree, this neural network has its own policy or probability, which is directly proportional to the number of times that particular state was visited. So this Monte Carlo tree search, or this tree, basically gives out its own policy, and this policy is used for training. So this policy pi is the thing that is given out by your neural network. Neural network gives out a policy pi. Using this policy pi, you build a tree, and this tree gives out its own policy P, and this policy P is proportional to the number of times that particular node was visited. This probability P is given back to the neural network, and the neural network improves its policy by bringing the policy closer to P. So this back and forth happens over several times, and then finally the algorithm would have been trained.
Now the two algorithms are considered adversarial here or cooperative? One is MCTS algo, which is improving, and neural network is improving. Are they cooperating or adversarial in nature?
No, they are cooperating.
Adversarial. Okay.
They are cooperating with each other. Yes.
Okay.
So each simulation of the tree is by selecting an edge with a minimum action of Q plus an upper confidence value. So Q plus U, the upper confidence value is just what we saw. This entire thing, Q plus U, both of them is used to select a node, and you also have a stored probability, and the visit count for every node is calculated, and the leaf node is expanded, and the associated position is evaluated by the neural network. So neural network gives out P and V, and this vector is also stored in your outgoing edge of S, and this action value is backtracked. This action value V, whatever you got, is backtracked all the way up till the top, and then once the search is complete, these search probabilities, or this P, whatever you see, is returned. And there is another hyperparameter over here, 1 by tau. So n is the visit count of every node. So that is the probability of the tree, whereas pi is the probability of your neural network. So when the tree gives out its own probability, it is to the power 1 by tau, and tau is a hyperparameter over here, which they called it as temperature. And based on this, the neural network has been trained. So I have a quick summary for us to understand. You start with a set of random weights, and you assign P and V values for various states. So for various states within the neural network, you just for various states in the Monte Carlo tree, you just assign these values of P and V. And based on this, the tree builds with some initial state while balancing exploration and exploitation. And when it encounters a new leaf node, it uses the neural network to predict the values for that new leaf node. Q and N are at that point 0. And then there is a back propagation which goes all the way up and updates these values of all the upper nodes. And this way the whole tree gets built out. This algorithm is kind of really very complex, and in the paper I have given lots of details, but then as a part of this session now, I'm just trying to give an intro. Like most of you might be curious on how you are able to build a program for such a huge game, which is much more complex than chess. You can refer to the paper that I've shared. So the paper covers a lot more details, and if time permits, sometime I'll be able to probably explain it in detail. And if you would like to implement this, you can do it for simpler games like tic-tac-toe or Connect 4 or Connect X. There is an ongoing challenge in Kaggle, so you can just try it on one of those environments. If you have any questions, I would be happy to take.
So Shubha, where are we? I lost it for a moment.
Okay, I have explained this, but then this is just a brief intro on how exactly is does the algorithm work, especially if you're curious to know what was the logic behind AlphaZero or AlphaGo 0. But then the paper covers more or less all the details of what you need to know with complete formulas and complete loss functions. So this was just an intro to that. Probably if I have it'll require a complete 2-hour session for me to completely go through that paper. So they have any questions, they can feel free to ask.
Yes, so I have shared the paper link in the chat. All of you can see, you can download the PDF paper, which has a lot more details on this. So this was just an intro session because it's a huge topic. It needs a very long session to explain it in final detail. So audience, any final questions for Shubha here? So, this is actually the last module in our RL course, which Shubha has developed for CellStrat, and it is probably the most complex module of the RL course. So clearly, it does need prior knowledge of RL in an extensive manner, because this is quite a very, very complex algorithm, but quite fascinating as well. I think the fundamental concept is there is a MCTS tree search algorithm, and there is a alpha zero neural network, and they are guiding each other in a way, so that removes the need for a human feedback loop, and that's why it was able to train itself, because there are two algorithms which are cooperating and sort of helping each other improve, and unlike other algos where a human feedback loop or supervised level is provided, and here on its own, by playing the game repeatedly, it is able to master the game, and between the two algos cooperating with each other. So that is, I think, the fundamental message here. Am I right, Shubha?
Yes, Vivek.
Okay, so any final questions, audience? There's some good feedback coming on the questions tab, but any other questions? So the paper has been shared, and it will be also available on CellStrat site with all the other papers. As I said, we have an excellent course in RL, which you can inquire about and which Shubha has prepared, and we are doing a live batch as well. Okay, so any final comments, Shubha?
No, Vivek. Thanks for the opportunity.
Okay, thank you all. So thanks a lot, Shubha. Next, we'll be going to our last session for the day, on meta learning. And so I'll be bringing Bhavesh Sardagiri, our AI researcher in the space of AGI. Just a moment. Bhavesh, I'm making you presenter now. So, okay, so with that intense presentation, next one is equally interesting. This is on meta learning, a path to artificial general intelligence. And we have here Bhavesh Sardagiri, who's an AI researcher with CellStrat Lab and also a team lead in our product team. And he's also developing our webinar series for, artificial general intelligence, as well as an upcoming course in this area. So Bhavesh, welcome, over to you. You kindly, the recording is on, so you're all set.
Yeah. So hello everybody, my name is Bhavesh, as Wilksa told you, and I'll be presenting a review on meta learning, on an introduction to the meta learning. And yeah, so this is actually somewhat related to AGI in the sense that meta learning can be used for generalization and adaptation. So the contents of this session are going to be like basics of what meta learning is, what are the types of meta learning, and the 3 approaches to meta learning, and then just a summary. So in general, meta learning is about designing models which can like adapt to new tasks efficiently. Like we don't need to fine tune it a lot. Like even if we have to do it, we don't need to like fine tune it a lot. We just like the models are built in such a way that they can learn and adapt to new tasks easily. So for example, you can think of if a game playing bot is trained to play a shooter game like PUBG. So PUBG is a first person shooter game. It should be able to generalize to Call of Duty. It is another game, but because the concepts are same, right? Both have guns, both have players, both every player the player has to kill the opponent. So the concept is same. Only the visual appeal might change. But meta learning is about such that we can develop AI which could generalize in such a manner, or maybe a robot which has learned to walk on flat land, flat and perfect land. It should be able to walk on some ragged terrain as well, because the concept of walking is going to remain the same regardless of whether it is a ragged terrain or a flat terrain. And then similarly, image classifier, which is trained on dogs, should be able to recognize any other animal given just a few examples of what the animal looks like. I mean, let's say a cat or an elephant or a tiger, because all have like 4 legs. The basic structure remains the same, right? So in general, the applications of meta learning are very wide. So they go from hyperparameter optimization to neural architecture search, and few shot learning is like one of the primary applications of meta learning. So in few shot learning, we train a model with very few examples. So in general, we usually, like if you want to train an some model in supervised learning, we need to have like hundreds and thousands of training examples, right? In few shot learning, it is reduced down to like 10 or 5 examples. That's it per class. So that kind of tasks, meta learning is very applicable. And also the reason it is also driving research towards AGI is because of the fact that it can generalize and adapt. So hybrid versions of algorithms which utilize meta learning and symbolic AI and other reasoning methods and RL as well. All these hybrid versions do use meta learning, and even in RL, meta learning is applicable. So meta reinforcement learning it's called. So we'll talk about the 3 different approaches that we could achieve meta learning. So meta learning, there are 3 basic approaches. One is metric based, model based, and then optimization based. So in metric based, we learn an efficient distance function. So it's like learning to match similarity. It is so the basic aim of metric based meta learning is so that we can learn a similarity function. So just before I proceed, I just wanted to point out that meta learning is like learning to learn. It's also called learning to learn. The reason being that you train a AI such that it can learn efficiently. So like the goal is to learn efficiently such that during testing phase, we could use very less examples. Like it can easily adapt and generalize to other tasks without a lot of training. So the goal during the meta training phase is to learn quickly, like learn to learn quickly. So it's like training a trainer. So that's why it's also called learning to learn. Yeah. So in metric based meta learning, so the core idea is similar to like a nearest neighbor algorithm. So, or let's say kernel destination. So the basic aim is that we want to, that we want to maximize the probability of two images in case of supervised learning, two images being similar, right? So we train it in such a manner such that the similarity is increased. And yeah, I guess maybe there's a question. Do we use graph networks for meta learning? Yeah, it actually like meta learning in general, the concept can be used for any sort of network. So so I'll just first go on to the problem and then we'll come back to this slide. So let's say there are two sets here. So one is the training phase and one is the testing phase. So I'll just change the file. So in the training phase, we have what is called a support set. Okay, this is called a support set, and then we have a query set as well. So in the support set is basically like a sample where we have a few images for each class. So for example, for cats, we have 4 images, 1, 2, 3, 4. And for similarly for birds, we have 4 images, 1, 2, 3, 4. And then we have a query image, which and the aim of the algorithm is to match this with the correct class. So it has been given 4 examples of each class, and it has to learn to match it with the correct class. So this is sort of like similarity measurement. So you are trying to learn a similarity measure such that you can match this particular bird image to this particular class. And similarly, like there are flowers and bikes. So the basic idea in few shot classification for metric based meta learning is that you divide the entire data set into multiple tasks. So what does that mean is, for example, if your total training data set had like 100 classes, you would sample 2 classes at a time. So in this case it is 2 classes, right? You only have cats and birds in this one sample. So you like create some mini data set sort of thing. So you just create some mini data sets, which each data set containing some random class from the total 100 classes. So each mini data set contains a maximum of 2 classes like cats and birds, and then flowers and bikes and so on. And during the testing phase in the real world, when you want to train it on a new data set completely, you do the same thing. You give 2 classes and give each 4 images for each class, or maybe 5 or whatever image that is available. So in general, the future classification problem is modeled by breaking down the total data set into a multi-class into multiple tasks, so into multiple subtasks. So if you have 100 classes, each you'll create mini data sets with each data set containing 2 classes.
So this is not the same as mini batch learning, right?
Yeah, this is different. In mini batch, we have like a random sample of containing all 32. You'll have 32 rows of data, right? In few shot classification, instead of that, you'll have 1 row, but each row will contain sub rows in it, 1 for each class and whatever data. So each row is actually another data set in itself. So even if you batch multiple mini data sets, it will still be 32, but each row of that batch will contain another data set. So it's like a data set in a data set. So there is a big data set, and inside that you have multiple small data sets. So this is just to simulate just to simulate multiple data sets or multiple tasks, because we are training the algorithm to multitask. So the basic aim here is to multitask, to be able to learn a lot of different tasks, and so such that when the new task comes, it is able to do the same for that as well. So you're trying to multitask thing. You're trying to learn to multitask. Yeah, so coming back to the same formula. So here, how do we find the similarity is basically we create a function or some value, k theta or some kernel function. It could be anything. There are different algorithms to do that. The basic aim is so that we can increase the probability of the query image being similar to the one in the support set. So we want to So we want to maximize this. We want to maximize the similarity of this bird image with these 4 bird images. So we train the neural network to do that because each row of data is like another data set in itself. So to achieve this, we have a few algorithms. So here I have put 4 algorithms. One is CME network, also called convolution CME network. Relation network, matching network, and prototypical networks. So CME's network is basically a binary network. So the output is binary, whether similar or not, 0 or 1. So it takes 2 images at a time and checks if both the images are similar or not. And and the reason it is called CMEs is because like to show like CMEs twins sort of thing. So, and on the other hand, like we have relation network. Now so CME's network was only taking 2 images at a time, right? Relation network is a bit different. It takes like multiple images at a time, all the images in the support set, let's say, and it does things like, let's say we have 3 images in the support set, and then we have 1 query image. What it will try to do is it will try to find a relation score for this with this and this and this. So it's like regression. So in this case, relation network is performing regression to find the most similar images. So for one image, it might give a score of 0.9. For another image, it might give 0.3. For another image, it might give 0.2. So here the loss function is actually mean squared error. So we are trying to regress the relation score. So the advantages of this is you get sort of like a scale as to how similar a particular image is, or how similar is a particular image is not to some other image. So you get that scaling thing with relation networks. And currently the state of the art among these is actually relation network only. So we'll not go into details of how this algorithm exactly works, but this is like the basic idea that you can think of relation network as multiple CMEs networks coupled together. So you have this image, you have this image, you have this image. You just put all the feature vectors together and output a score. So relation network is like a CMEs network, but at multiple images scale. And the only difference is CMEs is a binary cross entropy loss, and relation network has a mean squared error loss. We are trying to regress here. CMEs is trying to classify here whether both are similar or not. On the other hand, we have matching networks. So the concept here in matching networks is also similar. We have multiple images in the support set, and we are trying to match the query image with the correct one. So here the goal is again cross entropy. It is also again similar to binary cross entropy, but in this case there are multiple images, and it also uses LSTMs with LSTMs to actually match the images. So it's not just convolution networks, but there are LSTMs as well helping the convolution networks match the images correctly. The reason we are using LSTMs is because if you just independently try to find the similarity between every image in the support set, you are not taking into account the similarity amongst the similar images. Let's say a dog and a cat. So there are some breeds of dogs and cats which actually look quite similar, right? So in that case, if we just use a relation network, the chances are it might give both the dog image and the cat image as similar because both breeds are looking quite similar. But a matching network, because it is using LSTM, it will go through all the images in the support set and create like a context vector sort of thing. So it creates a context like how similar is this particular image to another image in the support set given the context of the other images. So it is taking into context account other images as well while finding the similarity score. Well, theoretically, matching networks should like outperform all these networks because it is taking a context vector as well. Although like experimentally relation network still performs better even though it doesn't take into that extra context vector which matching network has. And on the other hand, there is prototypical networks. So on the fourth thing. So what this does is let's say we have a few images, for example, for class A, 3 images for class A and 3 images for class B. And we have a query image. Okay, this is a query image which belongs to class B. Now, what this prototypical network does is it takes the feature vector of all the images in the support set and finds the average. So creates some sort of like a general feature representation of the class, and it does the same for all the classes. And then it tries to find the distance of this query images feature vector to this or this. So whichever is closer, then that it belongs to that particular class. The concept is quite simple, but the results are effective enough. So the basic idea is just to take the average of all the training examples, all the support set examples, and then make a feature vector which acts like a general feature representation of a class. It's also called a prototype, like in the paper. It's this particular vector is called a prototype of the class, and then we just try to find the distance of the query image with the prototypes, with whether it is closer to the A prototype or the B prototype. So this is how in general metric-based algorithms work. They try to find the similarity between the images, and all these 4 algorithms are like, although they are quite similar in nature, the results are still a bit different. The approaches are different, but at the end goal remains the same, to learn to find the similarity. Is this similar to cluster networking for unsupervised learning? Yeah, this is actually similar. So that's why actually in the beginning the core idea is like I mentioned, that the core idea is similar to nearest neighbor algorithms. So k-means, KNN, and all these algorithms. The idea is similar. The only difference is instead of unsupervised nature, it is supervised in nature, and we use neural networks as a general machine. So yeah, so this is actually similar to clustering algorithms. So this is, but just on a neural scale. And so that was the metric-based meta-learning. If you have any questions, feel free to ask. And if not, we can proceed to the second approach, that is model-based meta-learning. So in general, when you try to solve any problem, what do? Like let's say you want to solve an algebraic problem. Let's say I want to calculate 2x plus 3y is equal to 4. I want to calculate that. I don't know the values of x, I don't know the values of y, but my goal is to calculate those values. What I would do is I would try to have a working memory sort of thing, right? In a brain, we have a sort of like a working memory where we keep the operands and operations and everything in our mind, and then match them and mix and match them, operate on them, and do all sorts of operations on them to find the answer. A more better example is the computer. In a computer, we have the RAM where all the operations operate, and then we have the storage, and then there's the processor. The processor of the RAM and everything, the instructions and all the data that is required to perform an operation are brought to the RAM, and then the processor operates on all the information that's in the RAM and to get an answer. So model-based meta-learning is also quite similar, and it is also referred to as memory-augmented neural networks. So the core idea is similar to a computer. So there is a neural network which is sort of like the processor in our computer, and then there's a memory which sort of is like the RAM in our computer. So there is a explicit external memory bank in a memory augmented neural network. So in general, LSTMs also have memory, but it's like implicit, like the memory is internal and it comes and goes as data come, like as you give an input, the memory stays for some time and then goes, and then when you add some another input, that memory goes away, unless you just dump the same thing in repeatedly. And also LSTMs don't perform well on long sequences. If you have a very long sequence, LSTM loses contact, loses track of all the sequences, and same goes for RNNs. On the other hand, memory augmented neural networks don't have that limitation. They also work with sequences, like they can be used, they are mostly used with to operate on sequences like LSTMs. But the difference is that memory augmented neural networks don't have a limitation on how long the sequence can be, because they don't have an implicit memory, rather they have an explicit memory bank. So it's a separate memory location where all the information is stored in its own manner. So it's not like you just put a number in a list and then just store it like that, but it performs some operations and uh, puts it on the memory and then tries to read from that memory and operate on it and process it to get the answer. And because it doesn't have to like maintain an internal memory, uh, the only limitation is how big can you keep the external memory. So like, memory augmented neural networks can work on uh, longer and larger sequences. But when compared to transformers, so the latest, like just last few years, and we have been seeing the emergence of transformers. So transformers are like outperforming every bit of area. Like it has given some good performance in image as well as language, like mostly language, but image as well. But transformers consume a lot of memory, like they're quite computationally intensive, but memory augmented neural networks are not computationally intensive because they don't have to maintain an internal memory. They just have a simple neural network, and then they have a completely external memory bank where it can store data that store sequential data and operate on it to get the output. So mainly there are like two types of memory augmented neural networks. One is the memory network, and then one is the neural Turing machine and the successors of that, like the differentiable neural computer. So these are so mostly memory network is not actually widely regarded as a memory augmented neural network. When we talk about memory augmented neural networks, we usually talk about the neural Turing machine. So the architecture of a neural Turing machine is quite similar to what in this illustration. So here, so there is a controller. So this controller is a neural network, and then it has two heads. So one is called a read head and another is called a write head. So, and then there is the memory. So this is actually a matrix. So this is just a simple matrix. So what this actually does is the controller uses its read head to read data from the memory and uses the write head to write data into the memory. So if some external input comes in, if I give it some external input, it's going to use the write head to write that information into the memory so that it can use it in the future. And then when it wants to process it and get the output, it will use the read head to read the information, process it, and then get the output. Now it does the read and write heads work with attention. So the basic concept behind how it reads or writes information to the memory is that it's powered by attention. So it uses attention on its head to selectively read from the memory. So if I'm asking about, let's say I'm making some calculations and I'm asking about a specific, okay, let's talk about a much simpler example. Let's say Q&A system. We have a big paragraph which has lots of textual data about some personality, and then we ask the birthday of that particular person. So the read head would actually has attention, and it actually specifically extracts the information from the memory which contains the birthday of that particular person in the passage. So it uses so this entire system is basically operated on the magic of attention. So in general, attention is like doing a lot of breakthroughs in all sorts of areas. So the transform is all powered by attention, no LSTMs, no RSMs, and everything. And even NTM is powered by attention. So yeah, so the basic idea is this, and basically uses the read head, processes their stuff, and then gives the output. So the neural Turing machine has a successor as well. It's called the differentiable neural computer. So it's a much better version of neural Turing machine in that it has some extra mechanisms in the memory. So it has something called a temporal linkage inside the memory, which can be thought of like self-attention. So similar to how you would have self-attention, the memory has sort of that kind of mechanism as well. And in general, neural Turing machines, where can they be used? Neural Turing machines are good with algorithmic tasks. So let's say you want to train AI to perform some given task with a very few examples. You can use a neural Turing machine to do that. Let's say you want to train it to solve a particular equation, or train it to do some repeat some repetitive task or anything, or do some any algorithmic problems can be solved with neural Turing machines. And neural Turing machines also have a sense of reasoning and logic to them, like if not like if not the reasoning and logic of humans, but still they have some sort of reasoning and logic embedded implicitly inside them, because they use attention to selectively operate on the memory and try to solve a problem. So yeah, so this was about memory augmented neural networks, where they have an external memory to operate upon. And also one of the reasons of why it is meta learning, why it comes under meta learning, is because it can generalize to new tasks easily, because it doesn't have to remember anything. It just learns to operate on a memory. So it doesn't actually have any knowledge embedded inside the network, but rather it relies on the external memory. So if you swap the external memory with some other data, you can use this for any other task as well. So if you have any questions, let me know in the chat. And yeah, so that was about model-based meta learning. So the basic idea in model-based was that we could create models in such a manner that could generalize and have some sort of knowledge and reasoning capability embedded in them. On the other hand, like, so we talked about metric based, we talked about model based, now we have optimization based. Now what these networks do is, the key in this particular approach is you try to optimize the neural network in such a way that when you want to fine tune it on a new task, you don't require a lot of examples. So optimization based meta learning can be thought of like transfer learning. You pre-train it on a lot of examples and then you fine tune it right in transfer learning. This is also similar to that, except the difference is in transfer learning you need a lot of examples, right? You need at least a few hundred examples to be able to perform well. In optimization based, it is reduced down to few short, so just 5 or 6 examples or 10 examples at best that you would need to like fine tune it. And even that fine tuning is very fast. You don't need to like train it for hundreds and thousands of steps. You just need 1 or 2 gradient steps. So that's like very few, like just 1 or 2 gradient steps, and you'll be able to fine tune it. So that's quite interesting, because it can learn, it can perform fine tuning in just a few training steps. Like MAML, the main algorithm that we'll be talking about today is MAML. So this actually can do it in just one gradient update. In just one gradient update, it can fine tune a network for a particular task. And we also have a code demo, short code demo of that. So, and then there is Reptile as well. So the basic idea behind MAML is, so during the meta training, so meta training in MAML is similar to how you would do pre-training and transfer learning, right? You take a ResNet, you train it on the image net, and then you use the resulting model as a feature extractor or as a initial parameters to fine tune it on a specific task, right? So similarly, we do meta training in that we try to find the optimal initial parameters. We try to find some initial parameter which is closer to all the new tasks. So for example, the best parameter for a fire, for let's say we pre-trained it on, let's say cats and dogs, just for simplicity's sake, cats and dogs. And then we want to fine tune it on, let's say, elephants and tigers maybe. And then we also want to fine tune it on maybe some other animal, like some bird, let's say, and human. And then similarly, we'll have some other task. So we try to find the optimal parameter such that when you just do one gradient update, it quickly reaches the optimal parameter location for that particular task. So usually MAML is just for one gradient step. You can just reach the optimal parameter location for the new task or the fine-tuned task. So during the meta training, you basically try to find some optimal parameters, which is closer to all the other task specific parameters. You try to find a generalized initialization of the model. So the problem here in MAML is also the same. It's similar to is also few shot classification. So you have a support set and then you have a query set. In the support set, let's say it's a two-way, two-shot problem. So that means you have two classes. So way means classes, and then you have for each class you have two examples, right? 1 and 2. So that's why short. So two short two-way class task. So for example, in the support set, we have dogs and then there are humans. And then in the query set also we have dogs and then humans. And then we have the labels. So what we do is in MAML, we train it on the support set and evaluate it on the query set. So during the meta training phase only I'm talking about, we do a single step gradient update on the support set images and the support set images, and then test it on validate it on the query set to get like a loss function to get the loss. So we won't be using the loss from the support set to update the initial parameters, but rather the loss from the query set to do that. So there's a small animation sort of thing for that. So basically we have some initial parameters, right? Like some initialization of the parameters. So we use these initial parameters to fine tune it on a specific task. So we, as few shot classification is like mini data sets, right? In our entire data set, we have multiple mini data sets. So for each, let's say there are 3 tasks. For each task, the optimal parameters lie in this dotted region, dot circle region. So what we do is we first fine tune it for the first task. So we use the initial parameters and fine tune it on for the first task. So the weights that are the fine tuned weights are called like theta. So theta dash 1. So just to signify that they are the fine tuned weights and not the initial weights. And then we use these fast weights to make the prediction on the query set. So we validate it and get the loss. So this loss is the one that we deal with, the loss on the query set. And then we repeat the process for all the tasks. So we do the same. We use these initial parameters, fine tune it, and then we use this initial again to fine tune it for the third task. So we do this. So now we have 3 sets of fine tuned weights, one for each task, which is closer to that task. So this task, as you can see, is closer to 1. This is closer to 2. This is closer to 3. Now we repeat the same process. First we take the loss from the task specific and just sum them up or just do an average, either way, and then use that loss to optimize the initial weights such that we could get a much more generalized version of the initial parameters that during fine tuning it can reach the task specific parameter regions quickly. And we repeat the same process again and again such that it becomes equidistant to all the other tasks, to all the tasks in general. So you can see we reach a point so that if we fine tune it again, it would easily reach the third position or the second position or the first position. So we try to find a point in the parameter space that is equidistant to all the tasks, such that if we fine tune it, it's easy to get there. So I'll just have a small code demo on MAML. Yeah, okay. I'll just run it. So this is basically on the OmniGlot dataset, the code demo. So the OmniGlot dataset is like MNIST. The only difference is there are a lot of classes, like thousands of classes, like 1600 classes or something. But for each class, there are only 20 examples. So I'll just show you the train script, just an overview. So in general, we just create the model. We have our meta model. We create the loss function, cross entropy loss, because it's a classification problem. And then we have two loops. So one loop is for the meta training phase and one loop for the fine tuning. So we fine tune for each task, get the loss, get the fast fits and everything, then validate it on the validation set, or let's say the query set, and then like collect all the losses, and then we optimize the main initial parameters with that loss, and we finally get a set of initial parameters which can be fine-tuned easily. So basically I already have trained the model, like I do have the trained version of the model. Now what I want to just demonstrate you is how you could use that trained meta trained mammal trained model to fine tune on, let's say, these images. So there are only so I have these images. So it's of digits. So this digits are not present in the OmniGlot dataset at all. So there are no numbers in the OmniGlot dataset. And yeah, so I just run these cells. We create the model and load our model. So we load the meta trained model. And now before fine tuning, I just wanted to show you the performance if we didn't fine tune it, like the original version. Without any fine tuning, the results are bad. So 30241 should be the answer, but the answer is 02014. So after fine tuning, the results will be much better. So we fine tune it. So as you can see, the fine tune train steps is just one. So we train it for just one single step. And then we again make predictions. And now you can see the results are perfect, like 30241, 30241. So this is how mammal works, like in general, like how mammal works in action. Like you can fine tune your trained image classification based models with just a very few examples and just a single image, single training step. I guess I have a question here. Will you be sharing the collab link? I'm not sure about that. The code is like in general available if you with CellStrat. And yeah,
This one we can share as part of the research day today. So I think it's available on your GitHub account, right, Bhavesh?
Yeah, it's available in my GitHub. So my GitHub is github.com/innovative.
The neural being is your GitHub, right?
Yeah, I actually changed it to my old username. It's here right
Okay.
now. Okay, in the live slide, I do have the code. So it's not even.
Oh, new name.
Like actually, it's my old name. I changed it to Nilvin and then I reverted.
Okay. Nerdy might. Okay. Dynamite. All right.
So yeah, so you can find the code on my GitHub. So at Nerdymite. So this is actually the code link, Nerdymite/mammal. If you do, you'll get the link. You'll get the code, and there's a collab link to run it as well. So I can maybe like put this link on the chat if you wish to. So it's in the chat. You can check out the code there. Yeah. So just to summarize everything, so all the exact details are available in the paper. So we don't have time to like cover every algorithm in detail. And then there is there is the course as well building up on top of that, where we go through every algorithm in much more detail. That's coming up in the future. And yeah, so to summarize, so meta learning basically deals with creating models which learn to optimize which learn to optimize itself faster and generalize faster and much more efficiently, which much more less training data and much less time, it should be able to generalize and adapt to different tasks easily. And metric based systems is about using a similarity function to achieve that goal. So you try to learn a similarity function such that it can classify the images easily without a lot of training data, because you're training to learn to find similarity. You're not training to classify it, but instead you're training to find similarity between any given set of images. So you have some support set and you have some query set, and you try to train it so that it can match the query set images with the support set images, regardless of what it actually means. So here we are not focusing on on the exact understanding of the concept in the problem, but rather trying to find similarities in them. Model based, on the other hand, specifically use an external memory coupled with attention mechanism powered by a neural network to generalize and adapt to different tasks. And model based these model based meta learnings are still in the research phases. They're still in their early research phases. So but the results are quite promising. Like the latest version, like the differentiable neural computer, has some great results. You can check that out on the DeepMind website. So it's done by DeepMind. And then there are optimization based meta learning algorithms. So these try to find an initialization of the weights such that when you fine tune it on a downstream task, you don't need a lot of data or a lot of time. You just do one gradient update and it gets fine tuned to that specific downstream task. Yeah, so this was the summary. And these were the references, all the original papers, Lilian Weng, and thank you. And if you have any questions, let me know. And if you have any specific doubts, you can contact me offline and we can discuss about it. And I think the paper link
Okay,
as
great
well.
session, Bhavesh. Yeah, you can just show the paper if you like quickly. I have shared the paper link via chat, so all of you got the paper link, but Bhavesh, you can choose to show it briefly.
Okay.
The PDF if you like.
So this is just the paper. So Vivek sir and I have co-authored it. So we just talk about metric-based meta learning and some extra figures to explain the meta training concept, and few short learning, and then model-based, memory augmented, and the reading and writing mechanisms of the neural Turing machine are also mentioned here. And then we have MAML, and then a paragraph on like how optimization based and transfer learning are quite similar in their concept, but optimization takes it a step further by reducing the number of training samples required very less and even the time required to do so. And then there's the MAML algorithm. You can go through this algorithm in detail if you want to understand it. And the code is anyway with you, so you can try to experiment it and tweak it and understand it much more further. And then there's a application side of where to use what, like in what particular situations you should use which particular type of meta learning algorithm. Like in case of image, if you are doing anything related to classification sort of problems, metric based meta learning is quite useful. So be it NLP or image, both versions. Model based are for mostly like it can be extended for image few shot classification as well, but they are currently more suitable for algorithmic tasks. And memory networks are good for NLP as well. So and in case of optimization based, MAML is actually general, so it can be used for NLP, vision, reinforcement learning, anything. So it's a very general and so in fact I think I missed it, but MAML stands for model agnostic meta learner, meaning that it can be used with any kind of model. You don't need to frame your problem into anything. Like you don't need a special type of model. You can use it with any kind of model to train it with. Yeah, so thank you for that. If you have any questions, let me know.
Okay, audience. So excellent session, Bhavesh. Audience, any questions? That was a very quick overview of meta learning, but it is like a 6 to 8 hour topic actually. This was just a summary of 3 webinars previously presented by Bhavesh. There are 3 blogs on CellStrat site, and this paper will also has been provided to you. But the paper is still a summary of the 3 blogs. The 3 blogs are quite long, and there is a lot of information. So, any final questions, audience? Bhavesh, any final comments?
No.
Okay, so audience, any feedback for today's AI Research Day or any of our sessions? Okay, so thank you, audience, for attending. Thanks a lot, Bhavesh. Excellent presentation as usual, and look forward to your upcoming topics on AGI, which are scheduled next month. So thank you all audience for attending and engaging, and we hope to do another AI research event like this in a couple of months. Next month we do have a AI product showcase where our product team will present a variety of healthcare AI solutions. Okay, so a lot more interesting content coming up. Thank you all for joining once again, and we hope to see you in our future sessions. I hope you enjoyed the AI research event today, which was the first of its kind from our portfolio. And we'll be repeating this maybe a couple of months down the line and inviting papers from our internal and external communities once again. All the 5 papers which were presented today will be available as PDF downloads on our website in 1 or 2 days. And we'll be expanding the research paper portfolio over time. So look forward to collaborating with all the audience here and interacting with the broader community. Thank you all for joining today, and we look forward to seeing you in our upcoming sessions. Have a good day and good weekend.